I want to zoom out. It's not zooming out. Okay. All right, so here's my f here. All right, now, I can write my f. Let's see if this, I guess I'm not plugged in. Let me get plugged in. I should be plugged in, but I'm not. All right, what's going on here? Come on. I should be plugged in. I don't know why it doesn't say I'm not plugged in. Oh, I know why. Because I did something. I think I did something. No, I should be plugged in. Right, let me see if I am plugged in. No, I'm not plugged in. Don't know what's going on. Oh, there we go, because I wasn't all the way there. I think I'm on. I saw something move, but okay. Oh, here we go. All right. So, all right. So here's my f. I can actually write f as here. Let's do this. F is equal to the sum m equals 1 to n. Sum L equals 1 to n. I can write it as this way, zk times a kl cl. All right, so now we want to find the gradient. Oh, shoot. We want to find the gradient of that. So let me write it again here. So that's actually going to be, so the gradient, I want to take the derivative. I'm going to need another index. Let's call it ddz. Let's see, I don't have a j, so I can do ddzj. Well, I want to do ddxj. Right? ddxj of this thing here. All right, now remember that ddxj is actually equal to ddzj. That's what you found. Right? Now ddzj dxj is 1, so this is just equal to ddzj. So that makes it easier. Are you seeing my screen?
Yes.
Are you okay with that step?
Yeah.
All right. All right, so we can pull the derivative inside. Okay. So I can take the sum m equals 1 to n, sum L equals 1 to n. 1 to n, sorry. And then here I have ddz times zk. I'm going to put the two z's together because it doesn't really matter. Actually, I'm going to put the a first because these are constants now. Now we're at the level of summation. These are just constants. They're not matrices or anything. They're just numbers. Okay. All right, now since a is a constant, I can pull that out. I can pull the AKL out like this. Then I have ddzj of zk cl. Okay? Now, there are really two cases. Now I can use product rule. At this point. So I can do this. So if this is going to be dzk dzj times zl plus dz, I can do it this way, dzl dzj times zk. Now again, I'm not worrying about the order because these are numbers.
Do you need that in parentheses, though, because of the A?
Yes, right, yeah, very good. Okay, now what about this? There's really two cases here. What are the two cases? dzk dzj. What is dz1 dz2? It's the same as dx1 dx2.
Oh.
Now you told me a little while ago what dx1 dx2 was.
Didn't we say it was 1? No, that was the other one, wasn't it?
No, it's not 1.
I forgot.
Well, think about it. Because you did tell me before.
Two cases.
You think about two variables. You will go back and think about the two variable case.
Mm-hmm.
Now you had to take dx1 dx2. You had to take dx2 dx1 when you did your computation. So what was it?
Oh, but that was only one case.
What do you mean it was only one case?
Oh, I was looking at the wrong sheet.
Okay. Well, you can look at your first calculation. Because you did take dx1, or you took dz1 dz2 or dx1 dx2 or something. You had 4 terms, right? In your first case, you had 4 terms.
When n was equal to 2?
When n equals 2, yes.
Yeah.
All right, when n equal 2, you had 4 terms, right?
Mm-hmm.
You had a11 x1 x1 plus a12 x1 x2 plus a21 x2 x1 plus a22 x2 x2. And you took the derivatives of those 4 terms. Actually, those are z's, not x's.
Yeah.
You took the derivative of those 4 terms with respect to z1.
Yes.
All right, so what was the derivative of a12 x1 x2 with respect to x1? I'm sorry, z1 z2. What was the derivative of a12 z1 z2 with respect to z1?
Sorry, what term? A11.
No, a12 z1 z2. Your second term.
Oh.
What was
Are we combining?
What was the derivative with respect to z1?
2A12Z2.
So how did you get that?
Check it with respect to Z1.
Okay.
And
But wait, but there's a Z2 there too. Why didn't you take the derivative of Z2 with respect to Z1? You'd have to use product rule.
I did it in my head. Sorry, that was like a teenage answer. Because it's a constant.
Well, Z2 is not a constant, but it is an independent variable.
Okay.
Do you understand the difference between constants and independent variables?
Well, you treat it like a
You
constant.
treat it like a constant.
Yeah.
So if I was going to have a function of two variables, the point is that when you're doing partial derivatives, you treat the different. You do treat the different. So if I take a function here, let's just take some function here, x, y, and z, or x1, x2, x3. I'll just take some bowl function here. Now the point is that the partial derivative of this, so this is f of x1, x2. The partial derivative of f with respect to x1 is what happens when you vary x1 and leave, oh sorry, that was x2, sorry. Well, I'll just do x2 then. df dx2 means you vary x2 and leave x1 constant. That's what partial derivative means. Any surface has two slopes, not just one. Right? If you're on a hill, there's not just one slope. You can go across the hill or you can go up the hill. Each one of those slopes is a partial derivative. Now, if you vary x2 and leave x1 constant, then you treat x1 as a constant. So in other words, if I just have the function x1, that means that dx1, dx2 is equal to 0. When I vary x2, I don't vary x1. x1 doesn't change.
Okay.
So that's a basic fact about partial derivatives. If I have let me maybe do a simpler example. If I have the plane, if I just do the plane here, let's just do the plane here. I'll just say here's a plane. So let's say x1 minus x3 equals 0. We're talking about planes in linear algebra, right?
Okay.
All right. Now, what does this plane actually look like?
X1 equals x3.
Oh, yeah. Okay. So I better to say x3 equal x1.
Okay.
Now I can say that x3 equals f of x1, where f of x1 equals x. You're writing x3 as a function of x1. All right. So what does that plane look like? Here I've got x1 and x2. What does that plane look like? How would you draw that?
Oh my gosh.
x3 equals x1.
When x3 is 1. Wouldn't it be just coming straight out?
It does come straight out, but what do you mean by straight out?
Straight out of x3?
You mean straight up? Straight up like this? Does it contain the x3 axis? Give me some points that it contains.
Well, when x3 is 0, well, it contains the origin.
Contains the origin.
And when x3 is, so that would be 1, 0, 1.
Okay, 1, 0, 1, that's in this plane here. So if I go out 1 here, I go up 1 here, so it's something like this.
Yeah, so it'll go
So it
that way.
It contains this line. It does contain this line, but that's just one line. What else does it contain?
We can do 404, so it would be C0C.
That's right, that's what that line is. But that's not a plane yet. That's not a plane yet. I need another direction.
Oh, you mean negatives?
Sorry?
That includes negatives.
If you go negative, that's still a line.
Yeah, that's still the same one.
So does it contain the x3 axis?
I want to say yes.
Well, that would mean that, say, the point 1, 0, 0, 1 would be on this line.
And it's not.
No. In fact, the only point on the x3 axis that's contained here is 0 equals 0, because if x3 is non-zero, then x1 would have to be non-zero, and then it's not on the axis. So nothing here. How about the x1 axis?
No, same reasoning.
How about the x2 axis?
Yes.
Yes.
Because x2 is always going to be 0.
Yes. So it contains the entire x2 axis. So it's a slanty plane passing through the x2 axis. It passes through the x2 axis. Actually, maybe we can plot this in Wolfram alpha. Let's see. Let's say I'll say x1. I have to do it this way, plus 0 times x2. Let's try that. Let's see if that will give it to us. All right, so he didn't give me a three-dimensional graph.
Well, you have to add the x3.
Well, let's see. Let me see if I can do this. Okay, let's see. Oh, there we go. There you are. So in this case, this here is the x2 axis here. This one is the x2 axis this way. The
Okay.
the x1 axis is this way. The x3 axis is straight up. I think the way they plot it, the 0 is in the middle. 0, 0, 0 is in the middle. But this is the x2 axis. Notice that as I move along the x2 axis, it's flat.
Yes.
If I move along the x1 axis, it's not flat. Right, it's a ramp. But if I want to go up the ramp, I have to go in the x1 direction. All right. So that's what I was trying to say here, is that if you have two different independent directions, if I have the function x3 equals x1, it's a ramp in the x1 direction. The x2 does not change at all. I mean, if I move along x2, nothing happens. ddx2 means that I'm moving. ddx2 means I'm moving in this direction. How does the function change if I'm moving in this direction? If I'm moving in this direction, the function doesn't change at all. So if I move in the x2 direction, x1 doesn't change at all. If I move in the x1 direction, x2 doesn't change at all. So that's kind of a basic intuition about partial derivatives. I don't know, there may actually be if I look up partial derivative on Wikipedia. Actually, let's look at images. Lousy images. I want a graph. I want a picture. Give me a picture. All right, here. This is a nice picture. See what he's doing here. He's looking at the slope as you increase x. At this point on the graph, as I change x, I have this slope. But as the x is changing, the y is not changing. So dy dx equals 0. dx dy equals 0. If I'm changing x, I'm not changing y.
Okay.
That's because the x and the y are your independent variables. You're considering that your function is a function of two independent variables. So that's how it works.
So then we're taking gradients and we're looking at each the gradient. So like the first one, we're just looking at the x,
Yeah.
and then we're looking at the y,
That's
and
right.
then we're looking at the z,
You're looking at each
and we're just seeing how the function moves.
That's right. All right. Now, so can you answer this question now?
Okay. So dz.
There's two possible answers.
So this one we are leaving K alone.
Well, no. In this case, you're leaving everything but J alone.
Yeah, everything.
Everything else but J.
So are you just saying like J can either be moving or not moving?
Well, I'm saying that when I take this, if I take the derivative with respect to z1, then only z1 is changing.
Mm-hmm.
So z2 is not changing. So what is dz2, dz1? Only z1 is changing, z2 is not changing. If z2 is not changing, how much change does z2 have? None. What is none in mathematics?
Zero.
What's dz3, dz1?
0.
Yeah, all right. So what's the answer?
0.
All right, but that's only for that's only if in some case. There's another case where it's not 0. What about if k equals j? Is it still 0?
Oh. So it's 0. K doesn't equal j. And if k equals j, then it will both be moving.
Yes. Well, that's the case you have down here, where your function is x1.
Mm-hmm.
So in Wolfram alpha, that would be the slope of this plane. I don't know if it's still there. It's not going to go back. Here, let me do this. What's the slope of this plane in this direction? It's no different from dx dx. It's the same thing.
Yeah.
What is dx dx? Sorry, we lost this. So what is dx dx?
Of that plane?
Anywhere. What is dx dx? I don't care about what plane. What is dx dx? If you have a calculus class and you have dx dx, what is that?
Oh, 1. Oh, 1. 1.
If I vary x1, how much does x1 change? If I vary y, how much does y change? Same amount.
Yeah.
All right, so there are two cases here. All right, so these two cases both apply here. Does that make sense?
Yes. I mean, it will. I just have to look at it again.
All right, well,
I get it.
I think you need to spend some time with this. Because I'm not
Yeah,
sure.
I
I'm
mean,
not sure you really
I
have the intuition yet. You have to get some intuition here. But there's some because it's not. I'm asking you easy questions and you're not getting them. You're not getting easy answers. So that just means that you don't have the intuition yet. All right, so I'm going to erase this part because this was just, you can see this from, well, I'll just put it off to the side. This is all something, so we're going to finish up pretty soon here. I think you need some time to think about this. But this is definitely worth thinking about.
Yeah, because we need this.
Right. Okay. So I'm going to look at the first term. So I'm actually going to break this up into two sums. There's no reason why I can't. Okay. So let's write this. Let's go back here. So let's do this. Okay, so I'm going to write this as two sums.
Yep. Yep.
Wait a minute. I made a mistake here. Here I have a M, and here I have a K. So what did I do wrong?
I think those M's were supposed to be K's.
Yeah, I think I made the mistake all the way back here. This is supposed to be a K right here. So let's just be a little bit careful. And that's a K. Come on. That's a K. That's a K. It's better to be careful. That's a K, but this is a K. This is a K. This is a K. Fine. This is a K. So all those are Ks. K, 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 K. All right. So you got two terms, AKL, and then this is going to be, I'm going to write the ZL first, times DZK, DZJ. Then I'm going to have plus the sum, k equal 1 to n, sum, l equal 1 to n, of a KL times zk times dz l dzj. Okay. Now, as I said, this is equal to 0, or it's only equal to 1. It's equal to 1 if and only if k equals j. This here is equal to 1 if and only if j equal L. Otherwise, it's 0. That's what this says right here. That term, that's either 0 or 1. Right? Now, so let me just give you the punchline you can think about. This actually has n terms, n different values for k.
Yeah.
It's only non-zero when k equals j. This just selects the j term. So this selects the j term from these k terms. This one selects the j equals L term. What does that mean? This sum goes away. K can only take one value, which is j. So that gives me sum. The k term, this k sum goes away, and then here the k becomes a j. And then this one, the L goes away, the L becomes a J. What did I do?
J.
Okay.
Wait, that should be.
No, that's right. All right, so let's so you can look back over this, but here I have L, here I have K, but those are just dummy indices. I can call them both the same thing. So I can replace this k with a L without changing anything. Because it's summation index. It's a dummy index. Just like if you have an integral with respect to x, you can just say integral with respect to y. It doesn't change anything. You can replace all the x's with y's. It doesn't change anything. So this becomes the sum, L equals 1 to n, AJL, CL, plus the sum, L equal 1 to n, ALJ, CJ. This is ZL.
Yeah.
This should be a ZJ. I'm
So
sorry.
so that
should be a Z. No, ZL. This should be a ZK. Sorry. My bad. That should be a ZK. This is ZK. So if it's a ZK here, it becomes a ZL here. Sorry. It becomes a ZL.
And then you just combine them. So it'd be.
So this is equal to. Okay, now if we know that ALJ equals AJL, then I can replace AJL, no, I'm sorry, I can replace ALJ with AJL. And that gives me 2 sum over L, AJL, CL. So the bottom line is that I have the derivative of f with respect to zj is equal to 2 sum over L, AJL, ZL. And that's true for every j. Now this is my matrix multiplication, so I can write it this way: df dz1, df dz2, df dzn is equal to, well, this AJL here I'm going to have A11, A1n times C1, Cn, and there's a 2 here. Okay, and that's just the same thing as A times C, 2AC. All right. So I think you need to look at this and try to understand this, what's going on here. I think you need to think about this, why this is true. I wish I could give you an exercise, but I can't think of one off the top of my head. If I can think of one, I'll mail one to you.
Yeah, I'll just look at it.
But you should look at this calculation. I think I'm going to stop the video, or at least I'll pause it.